Hello everyone, welcome to IMS GATE Academy. I am Atul Negi, faculty at IMS GATE Academy. So we are continuing our fluid mechanics course, right? And we have already started some of the topics parallelly in other subjects also, right? So in this fluid mechanics, we have covered up to fluid kinematics. And if I talk about in fluid kinematics, we have discussed velocity, acceleration, types of fluid flow we have discussed. Okay, we have discussed the fluid element motion, right? Basic motions regarding deformation, angular motions we have discussed, rotationality we have discussed, vorticity, circulation, all those basics of the kinematics we have already discussed. Yes, so now in today's lecture, we will be discussing regarding the stream function and the potential function, velocity potential function, right? So these functions are what very important, okay, and we'll see what is the significance of these functions also. Okay everyone, now let's start the lecture here with the topic velocity potential function. Okay everyone, now see, very important. So first of all, we'll define what is velocity potential function, okay, and we'll see how we can utilize these functions. Okay, so see, what is the definition here? Very important. It is a function defined as a scalar function of space and time such that its negative derivative, remember this one, the negative derivative with respect to any direction give you the velocity in that particular direction. That is what very important. Negative derivative with respect to any direction. So negative derivative of what? The velocity potential function. So if you take a derivative of this velocity potential function in any direction, it will give you the velocity. So just by knowing that particular function, we will be able to calculate the velocity at any location in the flow field. At any location, we can calculate the velocity just by differentiating this particular function. So remember, the function is defined in such a way only that if you take the partial derivative of that function in any direction, it will give you velocity. So it's for our convenience. With this function, I can define the velocity at any point, at any location, and velocities are known. Then easily I can calculate the acceleration as well, right? So this is what the advantage we are having by defining such kind of functions. Okay, so this functions makes our analysis very easy. Okay, so this is the point that everyone should understand here. Okay, now, so as I already told you, like function, it is represented by phi. Okay, and it is a function of space and time. So when I say space and time, what does it mean? It means coordinates x, y, and z. So these are the coordinates, right? Now, based on the definition, I will be writing some points here, right? What is the point regarding the velocity only? What is the velocity? U, already we have discussed, velocity will have a 3 components: along x, u, along y, v, and along z, it will be what? W. All velocity components will be writing according to the definition that is what given for the velocity potential function. Now see, so let's suppose first of all u, if I am writing, it will be minus dou phi by dou x. So that is what written na. If you take a partial derivative of a velocity potential function in any direction, let's suppose x we have taken with negative sign, it will give you the velocity in that particular direction only, right? Similarly, v minus dou phi by dou y and w minus dou phi by dou z. Right everyone? I hope the point is clear. Now see, usually a function of space and time, but I will consider a case when flow is steady, because that is what the most usual case it will be. Okay, most common case will be when we are having a steady condition, when the flow is steady and incompressible. So this is what the basic assumptions that we can take during our fluid flow analysis. Very important point. When the flow is steady and incompressible, in that case, your function phi will become a function of x, y, and z, right? So we are using this function in order to calculate the velocities. I hope the point is clear, right everyone? Now see, so this point you should remember. So this is along x, along y, and along z direction. So we are having actually like this. u velocity component, v velocity component, and w velocity component. And we have a function of phi as a function of x, y, z. Okay, everyone. I hope this particular point is clear to everyone. Okay, so this is from the definition only. Now we will see whether the continuity equation is applicable or not. Right? We will first check. So two things we will check first of all. Continuity equation, because the continuity equation has to be satisfied, then only it is a possible case of fluid flow. Always remember this particular point. We need to check the continuity equation. That is what the mathematical statement of principle of conservation of mass. It has to satisfy, then only it is possible to have a flow. Second point, we will check the rotationality. So two parameters we are going to check. Okay, everyone. So I hope the point is clear to everyone. Now next thing is what? Okay, you will be having a point here, sir. What this negative sign will represent? See, this negative sign will represent that the velocity, the value of velocity potential function decreases in the direction of fluid flow. The direction. Okay, so point is what? The negative sign signifies what? It will decrease, the velocity potential function is going to decrease in the direction of flow. That is what a very, very important point. Okay, everyone. Right. Now next we'll write here. Okay, so sometimes see, for a velocity potential function we will also define like potential flow. Sometimes we will mention it as a potential flow also. Okay, so you can mention here itself. Negative sign signifies or decreases in the direction of flow. Right, everyone? Okay, so negative sign signifies the phi decreases in the direction of flow. Now, second very important point, we have to check whether it is a possible case of fluid flow or not. As I already told you, we have considered a point here like steady and incompressible. Okay. Steady and incompressible flow we are discussing, and under this condition, what is our continuity equation? I hope you remember in the previous lectures we've already discussed about continuity equation. Okay, so continuity equation will be like this. See, continuity equation will be like this: dou u by dou x, dou v by dou y, dou w by dou z. This is our continuity equation whenever the flow is steady and incompressible, right? That is what a very important point. Okay, everyone, I hope the point is clear. Now we will apply this equation, okay, and we'll see whether it is satisfied or not. Now for that you should understand u, v and w values. We will just put these values in this particular continuity equation. Okay, so as u equals to minus dou phi by dou x, right? So it will be like this. Okay, so taking a negative sign out of this equation, it will become like this. It is like this. Yes or no? Now this actually it becomes our Laplace equation. Very important point. This equation will become our Laplace equation. How we can represent it? See, we can represent it like this. Okay, we can represent it like this. Okay, so this is the format of our Laplace equation. I hope the point is clear to everyone. So this is the Laplace equation. Now, in order to understand whether the velocity potential function is going to satisfy the quantity equation or not, we will check this Laplace equation. We will check this Laplace equation, right? Yes or no? We will check this particular Laplace equation. So, the velocity components are clear, and what is the negative sign signifies? The phi decreases in the direction of fluid flow, right? And applying the quantity equation, we got this Laplace equation. Now, very important point. If the Laplace equation satisfied, it means only the flow is possible. Okay, it's not like whether any potential function someone has given, you need to check whether it is satisfying the quantity equation or not, right? So, in order to check that particular quantity equation, we will see this Laplace equation directly, because we understand if you put the values of velocity components u, v and w, ultimately you are getting the Laplace equation. So, directly check the Laplace equation and you will get the answer. So, tell me everyone, is this point clear, yes or no? Right. Now, very important point. So, fluid flow, possibility of the fluid flow is what clear, because just Laplace equation we need to satisfy. Now, check the rotationality. Okay, check rotationality, very important point. Now, in this case, the very important point is that, so in the previous lecture only we have discussed the rotational components, right? For example, if I take omega z, and I hope you remember the trick that I have told you regarding what? The writing the angular components, angular velocity components. I have told you the trick in the last lecture. If you have not watched that particular lecture, please see those lectures also. Last lecture only we have discussed the trick regarding how to write angular velocity components. So, omega z if I have to write, so it will be dou v by dou x minus dou u by dou y, right, like this. Now, I will be putting the values of u and v values I will be putting in this equation. See what I will get. Okay. And here it will be plus. So, automatically the plus minus sign is there, so it will get cancelled out because both the terms are same only. This will get cancelled out. Finally, you are getting what? 0. So, automatically omega z value is coming out to be 0. And if similarly, if you check for omega x, omega y, both will get what? 0. Both the values will come out to be 0 only. So, similarly, if you check for omega x, omega y, also 0. This is the point. Okay, omega x, omega y, both are 0. So, finally, we should understand a very important point. For fluid to be called as irrotational flow, all the individual angular velocity components has to be 0. Even if one of the component is non-zero, it means it is what? Irrotational flow. It is what? A rotational flow basically, not irrotational. For irrotationality, all of the angular velocity components has to be 0. Individually, all has to be 0. So, here we will write the point here. For irrotational flow, omega x, omega y, omega z, both all are what? 0. And this is what we are getting in velocity potential function. So, it means by default the velocity potential function is irrotational flow. By default it is irrotational flow. Okay, so obviously it has been defined in such a way that it is applicable for only irrotational flow. It is applicable for only irrotational flow. So, rotationality we have checked, all the components we are getting is 0. So, finally we will note it down that point also. But see, this VPF, that is velocity potential function, is applicable for irrotational flow. Okay, I hope till now everything is clear. Any doubts? Any doubts till now? Okay. So now we'll summarize all the points here. We'll summarize the points. First point regarding the continuity equation. Regarding the continuity equation is what? The Laplace equation. So we'll write if VPF, in short I am writing velocity potential function as VPF. If VPF satisfies the Laplace equation, okay, if VPF satisfies the Laplace equation, then it is a possible case of fluid flow. Possible case of fluid flow. Okay, everyone. Now, so you need to remember whether the given velocity potential function will exist or not. So basically, the existence of velocity potential function depends upon what? The Laplace equation. Very, very important point. The existence of velocity potential function depends on the Laplace equation. If it is satisfying the Laplace equation, then obviously it is existing and it is a possible case of fluid flow, because if it is satisfying Laplace, it means it is what? Satisfying continuity equation. Very, very important point. So we should also understand, if it is satisfying Laplace equation, it means it is satisfying the continuity equation. That's why we are saying it is what? A possible case of fluid flow. Second point. So conclusions, I am writing here directly, conclusion points. Okay, everyone. So finally, so regarding the rotationality, what we got? VPF is defined for a rotational flow. A rotational flow, right, everyone? Very important point. So if someone says whether the velocity potential function exists for rotational or irrotational or both, so you should say it is always applicable for irrotational flow. Okay, because it is by default getting as an irrotational flow. We have checked, right? Omega z, omega x, omega y, all values are individually 0. So by default it is irrotational flow. So we don't need to check whether it is rotational or irrotational. It will always irrotational flow from the definition itself. But for the existence purpose, we need to check Laplace. Are you getting the point? For checking its existence, we need to check the Laplace equation only. For rotationality, we don't need to check. That we have already checked, right? So if question comes in MSQ or MCQ, whether it is rotational or irrotational, we will directly say irrotational flow only. Yes or no? Any doubts? Okay, now see what happens. Usually in the question they will confuse you, right? How they will confuse you? See, confusion will be there if you don't know the basic points that we have discussed initially. What we have discussed, steady incompressible flow we have discussed. Okay, velocity potential function we are checking for a steady incompressible flow. So already we have assumed it is steady and incompressible, right? That is there always. But after the analysis, we also get to know that it is irrotational flow. It is irrotational flow. Finally, in nutshell, we can say if velocity potential function exists, so then it is a steady, incompressible, irrotational flow. Right. So this point is not very important. If VPF exists for existence, we need to check the Laplace equation. Okay. So if VPF exists, then it represents steady, incompressible, and irrotational flow. I hope you got the point, right? So this point you should underline. Study incompressible and irrotational flow. So what actually VPF will represent? This is the point. Study incompressible and irrotational flow. So in nutshell, we have combined all the important points regarding VPF, right? Now, second important point regarding the velocity potential function is the line along which this function will have a constant value. So that particular line is what? Equipotential line. That point is what? That line basically is known as equipotential line. Okay, so we'll define like this. Okay, so what is equipotential line? A line along which velocity potential function will have constant value, right? The line along which VPF will have a constant value. So now for the steady incompressible flow, again I'm writing the point so that you will get to know, okay, these are the conditions that we need to take. And incompressible. Okay, for your VPF will be a function of x, y and z. But for simplicity, again I am taking the 2D flow I am taking. Steady incompressible and 2D flow. Okay, so usually we will define this for 2-dimensional flows just for simplicity purpose only, right? 2D flow I am defining. Now, very important point, equipotential line we need to calculate. Okay, so the line along which the value of VPF will be constant. So first of all, I will take the derivative of this particular VPF. So what I will be getting? Dou phi by dou x into dx plus dou phi by dou y into dy, as it is a function of x and y. Correct? Very simple point. Now dou phi by dou x value is what? Minus u. Remember the point. Minus u it will be there because u equals to minus dou phi by dou x. So dou phi by dou x value will be minus u. Right? See. Minus u dx plus minus v similarly dy. Now very important point, d phi value will be 0. Okay, as far as the equipotential line is concerned, right? So now see. So finally what you will be getting as dy by dx, very important point. What dy by dx you will be getting? Tell me. What dy by dx you will be getting? Minus u by v. Minus u by v you will be getting. Yes or no? Minus u by v you will be getting, and it is what? Slope of equipotential line. Slope of equipotential line. Right, everyone? So this will be the slope of equipotential line. So in the numericals, they will be asking like slope of equipotential line. They have mentioned some velocity potential function, right? So they can ask this point. Now, if velocity potential function is given, from that you can calculate u component, you can calculate v component. For that we have direct formulas. from that, putting those values u and v, you will be getting the slope of equipotential line, right? So such type of basic mathematics or calculation you can do it, right, on your own. So this is what the slope of equipotential line. So up to now everything is clear, yes or no? Up to this point everything is clear, tell me guys. So what are those things we have discussed in VPF? I'm telling you again, right? First point is what? For the existence of VPF, that is velocity potential function, it should satisfy the Laplace equation. And I've told you what is the Laplace equation already, right? Second, by default, the VPF is valid for irrotational flow. It means it is defined for irrotational flow only, not for rotational flow. It is defined for irrotational flow only. Very simple point. And in like if someone asks what VPF will represent, you will say, okay, it will represent steady, incompressible and irrotational flow. Right? That point is also important because in the starting only we have taken an assumption. It is, we are taking a condition in which steady flow will be there, incompressible flow will be there. Right? And this slope is valid when we are taking the 2D flow case. Okay, when we are taking 2D flow case. Now moving to the next part, guys, is the stream function. Okay, so now we'll see first of all the definition of the stream function, and then we'll see regarding its rotationality. We'll check whether it is what are the conditions under which it will exist. So all those points we will be discussing. So first the definition part. Okay, now if you see the definition here, defined as a scalar function of space and time, again that thing is what same, such that its partial derivative with respect to any direction, partial derivative, okay, if you take the partial derivative, right, with respect to any direction, now here there is a small change, it gives you the velocity component at right angle to this direction. Okay, it will give you the velocity component but not in the same direction but in the right angle. That point we should remember, velocity component at right angle to the direction. Initially it was in the VPF was along the same direction, but now it, in this case, it has changed to right angle of that particular direction. Very simple. Now see, function of space and time, right? So important point, the in VPF the notation is what, phi, here it is what, psi, right? So again, space basically means the location x, y, z. Now very important point, again see, we are taking steady incompressible flow. Again the conditions, okay, steady incompressible flow, that is what the conditions we are assuming. Okay, now see, okay, based on the definition we should write the velocity components, right, u and v. So for simplicity purpose I will be taking the velocity components for the 2D flow only, right? Okay, now see, first I will draw the coordinate system here. See, so this is along x, this is along y. Now you should understand, based on this basic geometry, you can say along x you will have a u component of velocity, along y it is v. So this will be minus x, so minus u component you will be having, here you will be having minus v. Simple mathematics, right? Now see, in order to write the velocity component, along u, so what they have told you in the definition, take the partial derivative with respect to any direction, gives you the velocity component at right angle to that direction. So let's suppose if I take the derivative, partial derivative of that stream function with respect to x direction, so what I will be getting? I will be getting right angle to it is what, v. I will be getting v. So dou psi by dou y. So I will be getting, simply it should be x only. Along x I have taken the derivative, but the velocity you will be getting at right angle. You will be getting velocity at right angle, right? Very important point. So dou psi by dou x, okay, dou psi by dou x I am taking, so I will be getting the velocity component at right angle, that is v only. Now if I take the partial derivative of the stream function along y direction, so I will be getting the velocity component minus u. Now you will say, sir, 90 degree can also be like this, positive u, but usually the positive sign we will take for the anti-clockwise sense. So we'll always take the angle in anti-clockwise sense. So it will be what? Minus u. So we have taken the derivative of stream function along y direction and we are getting the velocity in the right angle, which is what? Minus u. So basically minus u will be, or basically we should write like this. Simply we should write like this, minus y. Okay, or better you can again see, you should write like this also, minus u equals to. So it's your choice whether you want to write it like this or like this. So it's your choice. So I will prefer this one only, because you should understand u equals to minus dou psi by dou y and v equals to dou psi by dou x. But remember the definition. From the definition only we are getting these things. In this case we are getting negative sign only in u, not in v, because of the reason we have taken the derivative along x. So in 90 degree, what is the velocity component? V. In y direction, if I take the derivative of stream function, I will be getting what? The minus u, right? So that minus u sign will be there. So minus u I have written like this. So putting that negative sign here itself, so u equals to minus dou psi by dou y. So I hope this particular point is clear to everyone. Very basic point. So the velocity components are clear. Now as the velocity components are clear, next thing is what? Check for the existence, whether the stream function will exist or not. For that, what we will check? The continuity equation. Whether it is a possible case of fluid flow or not, we will check first of all the continuity equation. See, next question is about the existence. Existence of stream function, right? Now see, we'll apply the continuity equation. Continuity equation will be what? Dou u by dou x, dou v by dou y equals to 0. As we have taken already the 2D flow, so the z component will not be there. What is the value of u? Minus dou psi by dou y. It will be like this. Now automatically it come out to be what? 0. Automatically it is coming out to be 0. Yes or no? So it is what? Satisfying the continuity equation. Very important point. But in the case of VPF, that is velocity potential function, the Laplace equation is forming, right? Laplace equation is forming, but here it is automatically getting at what? 0. Automatically we are getting 0. So it means what? The stream function by default satisfying the continuity equation. So actually we should say like this, stream function is defined in such a way that it will satisfy the continuity equation. So whenever the stream function is there, it means it will be a possible case of fluid flow, but it is not same for the VPF, because we need to check the existence. In the case of VPF, we need to check the existence, but when we are checking the existence of stream function, by default it is what? Satisfying the continuity equation. So from here we'll understand, whenever stream function is there, it is already what? Satisfying the continuity equation. By default it is satisfying the continuity equation. So we should write it here itself, a very important point. Stream function is defined in such a way that it always satisfies the continuity equation. It always satisfy the continuity equation. Okay, so it will be always a possible case of fluid flow. Okay, everyone. So that point you should always remember. The stream function is defined in such a way that it always satisfies the quantity equation. That is what the possible case of fluid flow. It is always a possible case of fluid flow. So we don't need to check the existence of stream function, right? But now check for rotationality. Okay, rotationality now we'll check. See, for the rotationality, what we'll do, we'll check first of all the omega z component. As we have taken the xy direction, so obviously omega z we need to check, right? So omega z will be equals to half dou v by dou x minus dou u by dou y. Now it is half dou v by dou x. Now what is v here? V is dou psi by dou x plus like this. So now it becomes the continuity equation for the basically Laplace equation for the stream function, right? So in this case we are not getting this rotational component as 0 automatically like we got in VPF. We got the rotational component omega z, omega x, omega y, all the components we got as 0 in the case of VPF, right? So in that case it is already what predefined, like we can say as a irrotational flow, but in this case we are not getting it as 0 na. So chances will be there, either it will be rotational or irrotational depending upon the values of rotational component, depending upon the values of rotational component. So what we'll say, okay, for a rotational flow, omega z has to be 0, and if it has to be 0, this equation has to be 0. Right? I hope the point is clear. Now this is what we are having as a Laplace equation. This is what the Laplace equation. Correct? Now you should understand a very important point. In order to understand whether the stream function is rotational flow or irrotational flow, we need to check the omega z value. Omega z value, when we check, we got the Laplace equation. So when this Laplace equation is what satisfied, then only we will say it is for the irrotational flow. Otherwise it can be rotational also. But in the case of VPF, we have told it is valid for only irrotational flow because it is by default coming as the like omega z, omega x, omega y, all values are coming automatically as 0. But in this case it is not coming automatically as 0. So we need to understand whether this equation is satisfying or not. If it is satisfying, irrotational; not satisfying, obviously rotational flow will be there. Now we will write down the conclusion points regarding the stream function as well. So I hope up to here everything is clear. So for irrotational flow, condition is this one only. But if I talk about the existence, it will always exist. It will always exist as it is by default satisfying the continuity equation. So we don't need to check the existence of a stream function. In the case of stream function, we need to check for the rotationality. In the case of VPF, we need to check for existence. By default, VPF is irrotational flow. Stream function, check the rotationality. By default, stream function is a possible case of fluid flow. Yes or no, guys? Please tell me till here everything is clear, yes or no? So we should write a point here. Like for irrotational flow, this is there, okay. we should write it here. F stream function satisfy the Laplace equation if it satisfies the Laplace equation, then it is irrotational flow. Okay, but in general, the stream function can be valid for rotational or irrotational. It can be rotational or irrotational, right? So we should write it like this. In general, stream function may be rotational or irrotational, right? I hope the point is clear. So in general, the stream function may be rotational or irrotational, but for irrotationality we need to satisfy the Laplace equation. That is the very important point. I hope the point is clear till now. Now, as we have discussed, the line along which VPF is constant is known as equipotential line. Same thing we will do here for the stream function as well. So very important point. So line along which the stream function is constant, then that particular line is known as streamline. Okay, so we will write it here. Next thing that we'll write here is the streamline. Okay, very important point. Line along which stream function is constant. Right, now see, the stream function is a function of x and y, 2D steady incompressible flow I am talking, right? So I will write the condition again. Right, so these are basically the conditions. Okay, so now very important point. If I differentiate it, what I will be getting? Dou psi by dou x into dx, okay, plus dou psi by dou y dy. Now, as the line along which the psi value is constant, so d psi value will be what? 0. I will be putting, because I am writing this for the streamline, right? So for the streamline, this value has to be what? 0. Now, very important point, dou psi by dou x. What is dou psi by dou x? See, v value, and dou psi by dou y value will be what? Minus u. v dx plus minus u into dy, right? Now, the dy by dx, that is what the slope of streamline, will be equals to v by u. I hope the point is clear, everyone. So this is the slope of streamline. This is the slope of streamline, right? So this basic part at least you should understand. This much basic part you should understand, right? So this is the slope of streamline. Now see, we have discussed the streamline also. rotationality we have checked, existence we have checked, velocity components we have checked. Now we'll summarize all the basic points regarding VPF and the stream function. Okay, just a summary I will write it here for you, so that in a nutshell you will always have a quick revision for the stream function and the VPF, velocity potential function. So VPF I am writing velocity potential function here, and here the SF, the stream function. Okay, and we'll see what are the differences, right? VPF and here the stream function denoted by phi, denoted by psi. Right, now see, very important point. First, what are the velocity components? These are the velocity components. So generally 2D flow it will be there in our cases, so I am writing for 2D flow only. I am writing for 2D flow only, right? Correct. So this is the basic velocity component. Second, if it is satisfy the Laplace equation, it means what? Possible case of fluid flow. It means case of fluid. Okay, it means possible case of fluid flow, because if it is satisfying the Laplace equation, it means it is satisfying the continuity equation. So it means VPF will exist. That is VPF exists. But if we talk about here the Laplace equation for the stream function, it means flow is irrotational. Flow is what? Irrotational. So first two basic points, the basic difference. In the case of VPF, Laplace basically means the possible case of fluid flow, that is VPF exists, but in the case of stream function, it means the fluid flow is irrotational. Okay. Second point, always irrotational, or better we can write valid for irrotational flow. Okay, valid for irrotational flow. Flow only, and here may be rotational or irrotational. May be rotational or irrotational. Okay, may be rotational or irrotational, right? So these are the three basic differences that you should always understand regarding velocity potential function and the stream functions. These are the three major important points, right everyone? Correct. So these are the three major points. Now, okay, the slope of streamline and potential line, equipotential line, that we can also write it here. Okay, let's again add one more point. Is minus u by v, and here slope of streamline is v by u. Now if you see both the slopes, you will get one important point here. Now if you check both the slopes, and let's suppose if you multiply both the slopes, what you will be getting? -1, which indicates that the streamline and the equipotential lines are what? Orthogonal to each other, perpendicular to each other. Very, very important point. Okay, you should note it down here itself. So let's suppose slope multiplied by slope of okay, now see, minus u by v multiplied by v by u. So what actually you will be getting? -1. Now which indicates a very important point. This equipotential line okay, equipotential line and a streamline are orthogonal to each other, right? So this point is very important. Okay, but at the stagnation point, the velocity is 0, so it will not be valid at the stagnation point, right? So that is what a very basic thing. Stagnation point is that point at which the velocity of flow is 0. So this point is valid whenever there is no stagnation point. Otherwise, it is applicable for all the fluid flows, right? But it should be what? Steady, incompressible, and irrotational flow only. Okay, now one more point regarding this streamlines only. There is one more concept here, flow net. So flow net is basically a grid which consists of streamlines and a equipotential line. Okay, grid which consists of equipotential line and streamline. Equipotential line and streamline, right? Now how it will be, like, see. So let's suppose these are the streamlines. Like this it will be there. So let's suppose this is the equipotential lines and these are the streamlines. So like this, 1, 2, 3, like this you will take. So angle you will see as a 90 degree, but not applicable whenever there is a irrotational flow. Now one more important point. What are the conditions of flow net? Conditions of flow net basically are steady, incompressible, and also irrotational, right? So this point you should remember always. Why I have said irrotational? Because it consists of equipotential lines, right? And equipotential lines, it means the VPF function is there, and if VPF function is there, automatically it means irrotational flow will be there. So these 3 points you should understand: steady, incompressible, and irrotational. Right, everyone? Any doubts? Okay, any doubts? Okay, clear, everyone? So remember these 3 conditions. Under these 3 conditions only you can draw the flow net, and actually it represents the flow pattern. It represents flow pattern. It represents the flow pattern. Okay, everyone. I hope the point is clear. Now these 4 points basically are what very important. First point regarding VPF, the velocity components, and stream function velocity components I have told you, right? Second, the Laplace equation. Most of the time students will do a mistake here, or they have some confusion. Remember, Laplace for the velocity potential function is what? It means the existence of VPF. VPF will exist if Laplace satisfies for the VPF, velocity potential function. But in the case of stream function, if Laplace is satisfying, it means flow is irrotational. Both are different. Satisfying the Laplace in the case of VPF and in the case of stream function, both will have a different meaning. Both will have a different meaning. Most of the time student will understand, okay, stream function and VPF both are satisfying the Laplace equation, it means same. No, both are different. Please remember this point. Okay. And the last, it is valid for irrotational flow, and the stream function may be rotational, may be irrotational. We need to check it. In the case of a stream function, this point we need to check whether rotational or irrotational. In the case of VPF, we need to check whether it will exist or not. Rotationality, if we talk about rotationality in VPF, by default it is irrotational flow by the definition only, right? So I hope we have actually completed entire fluid kinematics. In the next upcoming session, we will do some PYQ from the kinematic chapter itself, and you will see whatever we have discussed regarding the fluid kinematics, it will be what more than sufficient, and we can solve all the PYQs here. Okay, and if there is any doubt, you can also ask me in the live session or in the comment box also. And see, whatever we are discussing, for that the PDF notes will be available in the Telegram group. Telegram group link is available in the description of this particular video, and you can join the Telegram group, and we will have videos. We'll have all the PDFs regarding whatever lectures I have taken in this foundation course. Right, everyone? Thank you so much.